Okay, so we're looking at the notes on projectile motion. We'll just read through these quickly. So when a projectile is launched into the air, the horizontal motion has a constant velocity. So what does that mean? When it has a constant velocity, we know A is equal to 0 and V is equal to U. So the final velocity is equal to the initial velocity because there's no acceleration. In this section, I'm going to start using this by subscripts to denote, so it's a H if you can read that. These are H's. So just to denote that they're horizontal compared to the vertical one. So in vertical motion, it has constant acceleration, the acceleration due to gravity. So on Earth, AV is equal to 9.81 meters per second squared down towards Earth. Okay, so these two motions are completely independent, so that, for example, a bullet fired horizontally should reach the ground at exactly the same time as another bullet dropped from the same height. So for that example, if you just had a bullet and you just let it drop to the ground, and you had another bullet and you fired it, doesn't matter what speed you fire it at, the amount of time it takes to get from our height to the ground, assuming the ground's the same height or the same distance, then the time it takes is equal both of them. So if that's 1, that's 2, then T1 would be equal to T2. Okay, and that's because we'll talk about forces a bit later, or that's the next section, but basically the only force acting on these is the force due to gravity. That's ignoring air resistance. So force due to gravity, that's the only force acting on it, so the only way it's accelerating is downwards. Okay, and we'll talk about this now. So for example, we will plot the path of a projectile launched horizontally with an initial speed of 10 meters per second. Its motion is a combination of a horizontal component, which has a constant velocity of 10 meters a second, and a vertical component, which is the same as the motion of an object falling. So just imagine dropping a ball from rest under gravity, a gravitational acceleration of 9.81 meters per second down. In the table below, show the horizontal and vertical distances travelled by the projectile at these times. So we'll say that this one is SH in meters and this one is SV in meters, so S horizontal and S vertical. If you're not used to using subscripts in labelling things, some people do get confused by these. They think that you're meant to times these together or anything like that, but they're just labels just to show that this is a horizontal component and this is the vertical component. And they've both got units of M, units of meters. We use both these, to calculate these distances we use S equals UT plus a half AT squared, and because SH would just be equal to U times T, because acceleration is equal to 0, and SV is going to be equal to a half AT squared, because the initial velocity is 0. So just imagine dropping a ball, initial velocity is 0, so that UT will cancel out. Okay, so horizontal displacement at time 0, it's going to be 0. Then if we got 0.5 times by initial acceleration of 10, initial velocity of 10 meters per second, we get a distance of 5, then 10, then 15, 20, 25, 30. So all our time has been multiplied by 10. Now with the vertical displacement, we substitute half, so half times 9.81 t squared, hopefully that fits in, 9.81 times t squared, and when we put that into a calculator, 0 times 0, it'll be 0, then it'll be at 1.23 meters down, and then it'll be 4.91 meters, we get 11.0 meters, 19.6 meters, 30.7 meters, and 44.1 meters. Okay, so now we're going to plot those into our graph here. So along here we have our horizontal in meters, and down this way we're going to have our vertical displacement in meters as well. So this is our 0 point, and this is also a 0 point. Then this will be 5 meters. This will be 10, 15, 20, 25, 30. And along here I'm going to make these 10, 20, 30, 40, and 50. Okay, so what I'm going to do first is plot our vertical displacement along the vertical axis. So 1.23, I'll try to do this as accurately as I can, about halfway for the second point. So each of these dots just represent a time. 11 is just beyond 10. 19.6 is just before 20. 30.7 is just around 30. And 44.1 is about halfway between 40 and 50. Okay. So now what happens is, in an actual, if you were to throw a ball, it's actually, the motion is a combination of both the horizontal and the vertical. So along here I'm going to match these up. So I'm just going to go along, and this will be our point. So if this is our first point here, then our second point will be here. Just imagine you're filming it and you're doing stop frames of a ball or something being lobbed. Along here we've got name. Okay, so maybe you can already see that this is kind of like a parabola, we call it, like if you've done quadratics before, shape of a quadratic. Okay, and the reason it has a shape of a quadratic is because of this t squared term, so it is actually a quadratic, but you can just see that it's a curved motion when we combine the two, and my curve hasn't gone through all points exactly, but never mind. Okay, so the key thing to know with projectile motion is a combination of both horizontal and vertical components add up to the motion, overall motion. Alright, so we have a question for class discussion, which is an interesting one to think about. So a plane drops a series of bombs. If you were to watch the bombs from the plane, would they fall behind the plane, stay with the plane, or get ahead of the plane? Ignore air resistance, so that means that acceleration in the horizontal is equal to 0. So I'll write that in, AH equals to 0, and assume that the plane continues to move with constant velocity. So for both the plane and the bombs, they will move at a constant velocity in the horizontal. So have a think about how that would affect, if you were looking down from the top of the plane, how that affects. You might want to pause it before I go into the answer. Okay, so assuming you've unpaused it now, let's draw in our planes. It's hard to draw on this one. Now I'll draw a bomb in here. Not a great bomb. Oh, there we go. So I've got a bomb and a plane, and then it drops it here, and it lands somewhere like that. Now, if the plane and the bomb were both moving at a constant velocity, so both the velocity in the horizontal for both of these has not changed, only the bomb's velocity in the vertical will have changed. So we can say that, and I know it says a series of bombs, but I'm just considering one bomb at first. So if we have one bomb, okay, so we have this bomb, and what we would expect is that the bomb would stay directly below the plane from where it was released. So if the plane dropped a series of bombs, let's say it was up here somewhere, a bit further as well, and it dropped another bomb somewhere, then that bomb would fall directly below it, and you'd get a series of bombs going bang, 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 depending on where they dropped it from the height behind. Okay, so we do expect the bombs to stay directly below the plane.